Should Rockville switch to bottled water? The Wolverine Worldwide, a shoe company in Rockford, improperly disposed of chemicals which have leaked into the groundwater. The state's drinking water limit of 70 parts per trillion is considered safe, while anything above 70 parts per trillion is considered dangerous. Officials believe the water in Rockford may be unsafe. They take a random sample of 200 households in Rockford. They find the average lead level, so I guess that's what the PFAs are. The average lead level of the sample is 70.5 parts per trillion. So what are the appropriate hypotheses? Well, first we need to think about the parameter. What is our parameter of interest? It's a mean, okay, so we need to define that. It's the average, mean, mu equals the mean, and I guess I need to say the population mean, because we're talking about a population parameter here. The population mean lead level in Rockford's water supply. So I'm just going to put in Rockford in parts per trillion. So we want to define, including units, whatever parameters we're going to use in our null and alternate hypothesis. Now the null hypothesis is that the water is safe. Okay, nothing's happened, there's no problem, there's no danger. So we're going to say mu is 70 parts per trillion. Our alternate hypothesis, we want to know if the water has become dangerous. They think it may be unsafe. In other words, they think that mu may be greater than 70, and this is what we're going to be looking for evidence for the alternate hypothesis. Now, when they conduct a hypothesis test, they get a p-value of 0.045. So what exactly does the p-value mean? Okay, so remember we did find this average, so this is our x bar. So basically when we find a p-value of 0.045, this is what the meaning is. Given that the mu is really 70 points per trillion, we got a sample, an x bar of 70.5, and the area on the curve beyond that is the 0.045. In other words, 4.5% of the time we're going to get a sample that is 70.5 or higher if the null hypothesis is true. So if the true mean lead level is 70 points per trillion, there is a 4.5% chance of getting a sample of 200 households with a mean lead level. I'm just going to put x bar because I'm running out of room. With x bar equals 70.5 points per trillion or more. And that's important because it's not just exactly that amount, but then area under the curve. Now, based on the p-value, should Rockford keep the current water or switch to bottled water? Well, we need to think, once again, we have our two explanations for this sample. Either this sample happened by random chance, or this sample actually indicates that the water has become unsafe. So how do we determine whether or not that we would say, hey, the water's unsafe and we want to switch to bottled water? Well, we look and see how likely this is to happen just by random chance. And 4.5% is unlikely given our null hypothesis. Okay, so I guess I should say a sample mean of 70.5 parts per trillion is unlikely. Only a 4.5% chance. If the water is really safe. So we're saying, given the water is really safe, it's very unlikely I'm going to get a sample with that particular mean. So I'm going to switch to bottled water. I'm concerned. Let's suppose this decision's wrong. Well, could it be wrong? Could I have gotten a sample with a mean of 70.5 or greater, even if this null hypothesis is true? Sure. I could have, that still could have happened. I could have gotten an unusually high sample. So it may be that I made a wrong decision. In this case, if I made a wrong decision, I would be requiring everybody to drink bottled water when they really didn't have to. So people are spending money on bottled water when they don't need to. Unnecessarily. Okay. Which is a consequence, not a horrible consequence, but it is, you know, especially if people are not well off, that could be a little bit of a burden. Given that the water is safe, how often would a wrong decision like this occur? Okay, so given this, that here's our model, and it's a correct model, we're going to make this wrong decision whatever percent of the time we say that we'd make a wrong decision, probably around 5% of the time. So if we set our alpha, if alpha equals 5%, and we would reject the null hypothesis every time p is less than alpha, then 5% of the time we would be wrong. Does that make sense? Because I'm only going to reject I'm only going to direct the null hypothesis if p is less than alpha. So any time that we would get 5% or less in this tail area, which could happen 5% of the time, I could possibly be wrong. Okay. Now suppose the p-value is 14%. Okay, so in other words, 70 and 70.5, and this is 14% instead. So I'm saying that a sample of 70.5 or higher, given that the null hypothesis is only 70, is going to happen 14% of the time. So in other words, this would not be an unusual sample to get, given the null hypothesis is true. This would fall under normal sampling variability. Now, if an individual household was 70.5, I'd be concerned because obviously we're concerned anytime we get over 70.5. But we're saying if I took lots and lots of samples, I would expect some of the samples to be a little higher than 70, some to be a little lower. If I'm only concerned about the average, this is not an unacceptable, not an unusual sample to happen. So this is a different situation where maybe my standard deviation is different. Okay, so 14% is not unlikely. Okay, so in other words, this sample could plausibly occur just by random chance. So if it can, then I'm probably not going to make the hard decision to require everybody to drink bottled water. Keep the current water. However, that's still a risky decision, and maybe you would say, hey, even with 14%, I may still go ahead and switch to bottled water because I would rather be safe than sorry, because the consequence of this decision in Part 7 is much worse. Okay, if we're wrong, people could get sick or die, maybe even, from the contaminated water. So we don't want to be wrong on this. We want to be right. And so notice that, we have two areas where we could be wrong, and in this case, one's clearly worse than the other. Number 7, the consequences in question number 7 is clearly much worse than this situation. So that in the next video, we're going to talk about that these two errors that we're investigating are called type 1 and type 2 errors, and we have to think about when one is worse than the other.